Welcome to Module 3 for the structural exam preparation for the AIA structural license exam. I'm Dilip Khatri, and today we're going to talk about bending moments. From our last module, where we were talking about the shear diagram, we're now going to extend that discussion to discuss the topic of bending moments. So the first thing is we want to understand what is a bending moment. A bending moment is the concept of applying a force and producing some form of rotation about a pivot point. And the definition of a bending moment is the force times the distance to the pivot point. The best example to understand bending moments is to think about a seesaw. When you have a seesaw, you have a person on one side and a person on another side. If the person on one side is 200 pounds, and we'll put some dimensions in here, let's say that our seesaw is 20 feet long and each side is 10 feet, and the person on this side weighs 100 pounds, what's going to happen is the seesaw is going to tilt because the load from the 200-pound person produces a bending moment of 200 times 10 feet, or 2,000 foot-pounds. The bending moment from the person on the right-hand side produces 100 pounds times 10 feet, or 1,000 foot-pounds. So the 2,000 supersedes the 1,000, and so the seesaw tilts, in this case to the left. But if the two people weigh exactly the same, and the distance is the same, in this next sketch, if it were 10 feet and 10 feet and the two people weigh exactly 100 pounds, then the seesaw will remain level. And that way we say that it's balanced. We can take this example and we could look at, for example, on shifting this seesaw. And the best example is for understanding if you wanted to lift a very heavy weight, and let me explain. Let's take the example of the seesaw and use our pivot point, and in this case what I'm going to do is I'm going to draw a beam, and here's our pivot point. We'll call this point A, and here's my beam, and we'll put a very, very heavy mass over here. And for right now what we'll say is, we'll say that this mass weighs approximately 1 ton. We'll say it's a 2,000 pound mass. And we want to lift that mass up. And the distance from here to the center of that mass is, say, 2 feet. And the distance from here to the applied load, we'll say for right now, is 20 feet. And here's where you can see the concept of bending moment, or what we call leverage, becomes very important. If I apply a load over here, because of the distance between here and the pivot point, and I sum the moments about point A, my moment is 20 times P, which is equal to 2,000 times 2. Because this is the moment applied from the weight, summing it about this point, point A, sum of the moments equal to 0. So 20P is equal to 2,000 times 2 is 4,000 foot-pounds. So P, in order to lift that weight, would be 4,000 divided by 20, which is 200 pounds. That means that I can lift a weight of 2,000 pounds by applying a 200-pound force 20 feet away. That's the concept of bending moment, also known as the principle of leverage. And that's exactly the way we lift heavy cars. We use this principle of leverage in order to be able to lift a heavy car using a hydraulic jack. So bending moment is very important in terms of understanding a structure. So let's move from the seesaw to another simple example, which is I'm going to take two wood members. We'll make them two 2x4s. You can try this at home if you want. One 2x4 in one direction, and another 2x4 attached to it at 90 degrees. And I'm going to nail these two together. This is what's commonly referred to as a toenail connection. So this is a 2x4 and this is a 2x4. And we'll anchor this vertical 2x4, and you could do this by having two people hold it. And we'll throw a distance on there for right now. We'll say that this is 5 feet. And if I apply a load on this 2x4 to try to detach it from this connection, what I'm essentially doing is I'm pulling on this 2x4 in a tensile stress. This is causing a tensile stress. It is causing a bending moment in this 2x4, but if this is reasonably secure, it's going to be very, very hard to pull this 2x4 out of that connection, because you have these two nailed connections and you have this wood member coming into that other 2x4. If you try to pull it out, very difficult, because in order to pull this out, these nails have to pull out of the wood. So this is called a tensile load. But if I take the exact same structure, and let's just throw a number on it, let's say that this is also 5 feet, and now I apply a load at 90 degrees to this 2x4, I'm going to create a bending moment about this point. We'll call it point A. The bending moment is equal to P times the distance L. So we'll say, for example, we'll say that this is a 100-pound force. It would equal 100 pounds times 5 feet, or 500 foot-pounds, would be the bending moment. It will be very easy for me to break that connection. It will be very easy for me to twist those nails out. That's the power of bending moment. That's what a bending moment does. It's the force times distance causing a rotation about a certain point. So let's take that concept and move further with it and talk about shear and bending moment diagrams that you have to do for your exam. So let's now look at the principle of bending moment as it applies to beams. When we have a beam which is taking a load perpendicular to it, and we'll use the simple beam for starters. This beam resists the load by going into bending, and so the elastic curve looks like this. And if we took a picture of this and we blew it up, what's happening is the beam element, which started off as a rectangle, is going into bending, where the top part of the beam is going into compression and the bottom part of the beam is going into tension. And so these fibers in the beam are compressing on the top and they're extending on the bottom. And in the middle, nothing is happening. We call that the neutral axis. So the neutral axis, we have no stress. On the top fibers, we have compression. On the bottom fibers, we have tension. On the bottom fibers, we have tension. This is the standard performance of a beam under what's called positive bending moment. Positive bending moment, which occurs with the top being in compression and the bottom being in tension. So one of the first things we want to do is to do an example problem, and then I'm going to spend some time and talk about how do you know whether you have positive moment or negative moment. So let's do a simple example. Let's take an example of a simply supported beam. Same example we did in the last module with the shear diagram, except that now we're going to draw the moment diagram. So we have our simply supported beam, we have our reactions on the right and the left. We'll make this 100 pounds with a span length of 10 feet. And we draw our lines below that, one for the shear diagram, one for the moment diagram. The shear diagram, we talked about it last time, so I'm going to draw that in here. We did this in the previous module, so I'm going to skip over that. But as you may recall, our reactions are 50 pounds and 50 pounds. And our shear diagram is an even split between positive shear and negative shear. Now the moment diagram, we're going to do that now, but let's look at this beam and let's draw the elastic curve. The elastic curve looks something like this because you're going to have the maximum deflection occurring at the center, the midspan. The elastic curve tells us that the beam is bending downwards with a positive deflection going down. The moment diagram, let's do a free body diagram to understand what the moment is. So we're going to draw a sketch. Here's our beam at a distance x. We cut the beam here, and this is a distance x from the left support. The left support in this example is 50 pounds, which is our reaction. And we do not have any load as long as, of course, this is for x less than 5 feet, greater than 0. So our shear, as we determined in the last module, is equal to the reaction force, Ra, or in this case is 50 pounds. The bending moment will be the sum of the moments, and we'll choose this point over here as our point to calculate the bending moment, and we'll choose our sign convention clockwise positive. And so the bending moment is 50, the force here, times x equals the moment reaction on the right. So the moment is equal to 50 times x, which tells us that the moment is a straight line curve. This is a linear curve. And so the moment diagram is going to go up with a positive slope until it reaches the center. The value at the center is 50 times 5 feet, 250 foot-pounds. And the same thing will happen on the right-hand side, except that now on the right-hand side of the diagram, because now we have a negative shear occurring, the moment diagram will change. And so on the right-hand side, if we go back and do a free body diagram now of the right-hand side of the diagram, we have our left reaction 50 pounds. We have our downward force of 100 pounds, but now x is over here past the center point, and so our moment is plus 50x minus 100 times x, that's times this distance over here, which is x minus 5. So it's 100x minus 5. Gives us the moment past the center line. And if we simplify that, it's 50x minus 100x plus 50, or 50 minus 50x, which tells us that this is also a linear curve, which is going to go downward. And just like with the shear diagram, we always have to end up at 0. Now the shortcut, when you have to do this on a test, it's quite difficult to do the mathematics The shortcut is to remember that the value of the moment diagram is always equal to the area of the shear diagram. If I calculate the area, so let's write that down. The value of the moment diagram is equal to the area of the shear diagram. Let's see how that works. If I take the moment, well, let's go back to this diagram. If I calculate the area under this, in this rectangle, what's my area? This is plus 50, and this is 5 feet. So the area of this shear diagram is 250, and the area of this shear diagram is minus 250. Very important that the two are equal, because then when you add them, they have to become 0. So my maximum moment is 250, which goes up with a straight line, and then this is minus 250, which goes down with a straight line, because this is a constant and this is a linear curve. And the sum at the end is 0. So the formula for a simply supported beam, which you should always remember, it's a very simple formula. If our span is L, and for right now we'll make this L over 2, the maximum moment is PL over 4. Simple formula to remember. And let's try that out. So in this case we had 100 pounds times 10 feet divided by 4, which is 1,000 divided by 4, which is 250 foot-pounds. And that works exactly with our example. Now, how do we know that it's a positive moment? Well, in this simple example, we look at the elastic curve, and the elastic curve has compression on the top, tension on the bottom. That's usually the standard formula, but I'll give you a very simple notation to remember to determine positive and negative bending moment. It's a very simple rule that we use in the structural engineering business. Positive moment and negative moment. Positive moment occurs when the beam is shaped like this. We have compression on the top, tension on the bottom. Negative moment occurs when the beam is shaped like this. This is concave up, this is concave down. In negative moment, we have tension on the top, compression on the bottom. The rule that we use, very simple rule, is if the beam is happy, it has a positive moment. And if the beam is sad, it has a negative moment. This is the negative curvature, this is the positive curvature. Positive moment, negative moment. Simple rules of thumb for you to remember. Let's do another example. Let's do the example that we did in the last problem, the last module, which was the uniform beam. So we have a beam with a uniform load. And our uniform load is 100 pounds per foot. We have a left reaction, our right reaction. We'll set the span at 10 feet. And we drew the shear diagram in the last module. If you recall, that was a straight line shear diagram. And here's our moment diagram. Our shear diagram started with half of this load. Remember, we did the reaction calculations. It was 100 times 10 divided by 2, which is 500 pounds. The two are equal because the load is perfectly distributed. It's an equal load. So we start off with plus 500, minus 500, and the reason this is a straight line, because this is a uniform load. So the rule, short rule of thumb, is that the area of the shear diagram would equal the moment diagram. The other quick rule to remember is that the value of the shear is equal to the slope of the moment diagram. The value of the shear is equal to the slope of the moment diagram. So this value plus 500 and this value is 0 tells us that our slope of our moment diagram here is very steep and our slope of our moment diagram at the center is 0. Here our value of our shear is negative, which tells me that the slope of my moment diagram is negative. This is a positive slope, this is a negative slope. A 0 slope is flat. Let's calculate the area under this triangle. It's 1/2 of 500 times 5, which is 5 times 250, which is 1250. And let's understand that. Very simple calculation. It's a triangle. This is 500. This is 5 feet. The area under a triangle, 1/2 the height times the base becomes 250. And the units are foot kips because this is in kips, this is in feet. That gives us the area. This area under the shear diagram is equal to this maximum moment, 250 foot kips. And this area, which is exactly the same as this area, is the negative area, which is what brings this diagram down. And that's why the moment diagram looks like this. And the reason that it's positive is because the elastic curve is shaped like this. And if you remember our sign convention, that the happy face is a positive bending moment. That's why this is a positive bending moment. If I were to do the exact same problem over again and say I reverse the load in the opposite direction, if I reverse the load in the opposite direction and say the load was going up, my reaction would be going down. Then my elastic curve would look like this. My moment diagram would be negative because here my elastic curve is the opposite direction where I have tension on the top, compression on the bottom. And so my moment diagram would go like this. And this would be minus 250. That's if we reversed. And I'm just trying to show you the simplicity of understanding the sign convention on the moment diagram. Positive load going down in the downward direction, which results in a elastic curve as such, gives us a positive moment diagram. Let's do another example. Let's do an example with a cantilevered beam. So if we look at the cantilever beam, very standard example for understanding how bending moments work. We have our beam with our load P at a distance L. We did the shear diagram last time. In the last module, and the shear diagram was very straightforward. It was a positive shear going all the way across. This is P going up. And the bending moment diagram, so this is our shear diagram. It starts off at positive P, goes up, and then comes back down. The area under the shear diagram is PL. That is the value of the bending moment. And the bending moment is a linear curve that is negative because look at the elastic curve. This is our deflection delta. And our bending moment here is minus PL because the area under the curve is positive. We start at minus PL and then it goes positive in order to get to 0 at the end. We're always graphing from left to right. We always start from the left side and work towards the right side. You never want to start from the right side and work to the left because it will cause complications for your signs. So we've looked at 3 examples. We did the simple beam, which was the first problem. We did a simple beam with concentrated load. And then we did the simple beam with a uniform load. That was the second example. And then we did the cantilever beam with a concentrated load. Let's do one more example. We'll take the cantilever beam with a concentrated load and we'll add on a uniform load. The same example we did in the previous module, except now we're going to add this uniform load and draw the moment diagram for that. So the cantilever beam fixed on one end with a concentrated load and a uniform load. The uniform load will use 100 pounds per foot. The concentrated load of 100 pounds will make a span length of 10 feet. And we did the shear diagram on this. As you may recall from the previous example, where we started with the end reaction of 1100, it was a linearly decreasing curve, and then it dropped down this minus 100. That was our shear diagram from the previous module. Let's look at the moment diagram. The elastic curve is going downward. So the elastic curve tells us, using our sign convention, that this is a negative moment. The moment here is all negative. First, we can calculate what our moment is on the left-hand side. This is a positive shear area. It's a trapezoid. So first thing we do is we can calculate the negative moment here, which should equal the area under the shear diagram. But let's go ahead and calculate that negative moment. That negative moment is 100 pounds per foot, which is this uniform load, times the span, which is 10 feet, which gives us the total load, which should be looking upon as acting at the center of gravity, times the moment arm, which is 5 feet, which is the distance from that uniform load center of gravity to the end point A. That's what this part is. And plus 100 times 10 feet. And so this is 100 times 10, which is 1,000, plus 100 times 10, which is 1,000, times 5. 1,000 times 5, which is 5,000, which is equal to 6,000 foot kips. Let's do the area under the trapezoid. The area under the trapezoid is the sum of one triangle and one rectangle. So that area is equal to 100 times 10 plus 1/2 of 1,000, because this is 1,100, but we subtract here the bottom of 100. So this distance here is 1,000. It's 1/2 of 1,000 times 10, which is equal to 1,000 plus 1/2 of 10,000, which is 5,000, which gives us 6,000. So both numbers are matching each other. So the moment diagram is going to start off at minus 6,000, and then it's going to end up at 0 because that's the area of this triangle. And the slope of the moment diagram is going to start off as positive and is going to end up as positive because the value of the shear diagram is plus 1,100 and this is plus 100, so the moment diagram is going to look like this. And this is a linear curve and this is a second degree curve. And that's our moment diagram. And that brings this module to a close. Thank you.